MacMaths, let's do some math today. So this is lesson number 6 in this series, and it's the last part, and it's a quick part, and it's just looking at some simple combinations there. I've ticked the box there, see? Okay, let's get rid of my title page, those title graphics as I like to call them. Okay, so combinations of what we've been doing in the lessons. We saw in that very first lesson a 4 kilogram and a 2 kilogram weight, didn't we? Joined by a piece of string. So I've got a 2 and a 4 kilogram weight this time, still joined by a string, but this time over a pulley on the corner of a table, and the 4 kilogram weight is hanging over the table there. And so this is a combination really, isn't it, of horizontal and vertical and pulleys now. But actually not a pulley where they're dangling down either side, but you can see that one of them's on the table. It's going very simple. This is a very simple one, and I've actually gone for I've said a smooth table. When you see smooth in a question, it means no friction. I know that doesn't really exist, we've talked about that. The question that I'm going to get you to do after this yourself, I'm actually going to put friction in, so I'm going to see whether you think about how to put that force in yourself, but I will go through that question with you as well. And the question that I'm going to get you to go through after this, after my example, is a little bit harder than this, so I'm going to see whether you can work it out from what we've done. Okay, see whether you've progressed. If not, you know, watch it, have a go, but watch it, and I'll obviously go through it. So here we go. This is a system. It's released. The question would say it's released from rest. This 4 kilogram weight is going to start moving and down, and the 2 kilogram weight is going to start sliding along the smooth table because it's being pulled down by this weight. The whole thing is going to accelerate. So it's going to accelerate down in that direction, or that's going to accelerate with the same acceleration in that. And of course there's going to be tension in the string. Okay, and that is what we've got to find. We've got to find the tension in the string, and we've got to find the acceleration when released. And we do it exactly the same way as we do it when it's a normal pulley. So that means that there is here, if we put all the forces on, mg is acting down there, the weight of that particle, and that creates a reaction force on the surface there. It's not sort of falling through. But those two forces don't affect this horizontal movement on this one because it's a smooth surface. So we're going to largely ignore those. Well, we are going to ignore those. We do have, which we can't ignore though, is the tension, and the tension acts away from the body. So it's resisting this falling at free fall at 9.8 meters per second squared. And it's the tension that is pulling, it's acting away from this block. It's the actual force that's pulling the 2 kilogram block along. Acting down here, of course, is the weight mg of the 4 kilogram block bit. Okay, so what do we do? Well, I'll tell you what we do. What we've always said with pulley systems, we separate out the two sides. So if we look at this first one here, okay, for A, if we apply F equals ma for A, we can see that the force pulling it is T. There's no resistant forces like there is with cars and caravans, and the mass is 2, and the acceleration we don't know. So T is equal to 2a, as far as we can go with that one. With B, it's a separate. If we consider this one separately now, okay, and apply F equals ma, well, what's happening to it? It's moving down. So we're trying to work out that F, that net force. And the net force, of course, this is the driving force, the mg, the weight of it is pulling it down. And so the net force is mg minus the bit that's holding it back at falling at breakneck speed towards planet Earth, and that's the tension in the string. So that's going to hold it back a bit. So the net force is mg take away the t, and that's equal to the mass times the acceleration for A. Okay, and so for this one here, we've got mass times gravity, so 4 times 9.8, so I'm just going to put that in as 4g this time. Okay, minus t is equal to 4a. Okay, we can go straight to this. Is really easy because this is a simple equation, is that t is equal to 2a, and we know that the tension in both sides is the same, the acceleration is both the same. So now we're going to do a bit of substitution. I'll do my substitution in a different colour, do it in orange. Yeah, beautiful. Okay, so I'm going to take that t and stick it into there, and now I can say that 4g minus t, which is 2a, is equal to 4a. Now in the past, when I've done these other ones, I've put in g as 9.8, so I've worked that out. I've gone 4 times 9.8 in my calculator, and I've got that in, haven't I? So, but I've left it as 4g this time. Add 2a to both sides, so 4g is equal to 6a, and divide by 6 both sides, and the acceleration is 4/6 g, or 2/3 g. You want it accurate, that's what it is, 2/3 g. And of course, that is 2/3 of 9.8. So 9.8 times 2 divided by 3, and it gives me 6.53 meters per second squared. That's the acceleration. And I've got the exact answer in there, and if I times it by 2, I've got the tension, haven't I? Because I can put it into this, the simplest equation. The tension is twice the acceleration, and there we go. So double it, and I've got 13.06. So the tension 06, 13.1, and I've got that from there, just substituting it in newtons. So this system will have a tension of 13.1 newtons, and it will start to accelerate down at 6.53. Remember, if we cut that string, it would accelerate down at 9.8, wouldn't it, meters per second squared? But the tension, that tension is holding it back from dropping as fast as it would like. Okay, so I hope you sort of understood that. Just the one. I've made it a little bit harder, this one. A bit of equations of motion in there as well. Let's rub that out. Nice simple one, that one. And this is the question. I might have even got this from the textbook. Okay, there we go. So there's a question. The block on there, P and Q this time. That's 1.5, that's 2.5 kilograms. There is a frictional force, K. Okay, so there is a frictional force between the table and the surface. So think about where that goes. And this is moving down, and it travels, when it starts to move, when it's released from rest, this Q travels down 0.8 meters in 0.75 seconds. Okay, so not even sort of 1 second. Okay, find the tension in the string and the value of K. So put it on pause and have a go at that. Okay, and I'll go through that in a moment. Okay. All right, should we do that one then? Okay, here we go. Now this one, I'm doing this one cold because I haven't done this one before. So here we go. This is going to be fun then, isn't it? You should always plan these things beforehand, so I'm just going to move that up to give myself a little bit of room, make sure that is still in shot, and get up a little bit further. There we go. Okay, so let's redraw out that diagram. So I've got, there's my 2.5 kilograms, okay, and it goes over a pulley and down here, and there's Q. So 1.5 kilograms. Right, let's add all the forces on then. Okay, so let's go with green. That's exciting, isn't it? Even though I don't like it. I'm going to go with orange. Mg, tension, tension. Our frictional force resists, and I'm going to put Fr there, resists the motion, Mg acting down, and the reaction force there. We don't need those two on this one. Okay, And there's our table. Let's put our table in. There we go. So there it is. Now then, equations of motion. So 0.8 meters. Let's start with this one. So 0.8 meters in 0.75 seconds. So what have we got? We've got the displacement s, we've got time in the seconds, and we want, what do we want? We want acceleration. So which of the equations uses those? So this is s equals ut plus a half a t squared. Okay, so we're going to use that to find the acceleration. Now we know that s is 0.8 meters. The initial velocity is 0 because it starts from 0, so that all that is 0. That's handy. Plus a half of a times the t squared, so times 0.75 squared. Okay. So this bit here, we're going to go 0.5 times 0.75 squared. So 0.5 times 0.75 squared is equal to 9 over 32. So now I've got 0.8 is equal to, now in its decimal form all of that is 0.28125 a. That's 0.5 times 0.75 squared, and then divide both sides by that to get a. So 0.8 divided by all of that. So we go 0.8 divided by 0.28125 is equal to, the acceleration is 2.84. It's 2.84 recurring. So acceleration is 2.84 meters per second squared. There you go. Now we're in business. Okay. So from that now, we just, that aside, we just use that information and our Suvat equations to work out the acceleration. Once we've got the acceleration, let's add that in now. We know it's hurtling down there at acceleration is 2.84 meters per second squared. I've got that, and I can rub all of that out now. Got our acceleration. And now we just split it up into P and Q. So this is P and this is Q. So there's P and there's Q. Let's do them separately. Okay. So just what we did before. For P, F equals ma. This time you've got the tension pulling it, but there's a frictional force. So minus the frictional force is mass, which is 2.5, times the acceleration, which we've got. 2.5 times 2.84. So we've got that. So we've got tension minus the frictional force is equal to, and that's 2.5 times 2.84, mass times acceleration. So that is 7.1. There's one equation. We haven't got the tension or the frictional force. If we do this one, F equals ma, we've got the driving force is the mg, so we've got mg minus the tension, it's holding it back, is equal to its mass, 1.5 times acceleration, which is 2.84. Just worked out. So let's do this side, 1.5 times 2.84. This is exciting, isn't it? Is equal to 4.26. mg is mass times gravity, 1.5. 1.5 times 9.8 is 14.7 minus t. So t over to that side, 4.26 over to this side, so we get 14.7 minus 4.26. 10.44, so 10.4 newtons. That's the tension in the string. And of course, when we put 10.4 into there, okay, so we've got 10.4 minus the frictional force is equal to 7.1. You can see that the frictional force is 10.4 minus 7.1. So the frictional force is 3.34 newtons. There you go. So there we did that equations of motion for this first little bit just to work out the acceleration. So that aside, we used s equals ut plus a half at squared with those two numbers in to find out the acceleration. Once we got the acceleration, it was just separating out like we do with pulley systems. The difference next year is we're going to change the slope of that, and actually you sort of know this, don't you, from common sense. The heavier something is, the harder it is to drag along the floor. In other words, the heavier something is, the bigger the frictional force. And surfaces have, you know, if this was a heavier block, there would be more friction. So we have what's called a coefficient of friction. So there's another very simple little formula for calculating out the frictional force that is based on the weight of the block. In other words, the weight of the block is always equal to R, the reaction force. So it's based on R, but we'll look at that next year. Okay, so we found a frictional force. There was a little bit of friction in these lessons in the end, wasn't there? Right at the very end, and this one with a tension in the string. Okay, it's impossible to keep ignoring friction because it's there in everyday life, in every system actually. You know, even in a pulley there is friction. Okay, all right.